Okay, today we're going to be looking at the quadratic equation itself. We began tinkering around with it a little bit yesterday, looking at the y equals x squared equation, plugging some values into it, figuring out, and when we give the equation an x, what's our y going to do, and generating the graphs. Okay, so today we're going to be looking at the equation a little bit more in depth and look at a few particular values that can also show up in the equation. Okay, so we've got our calculators. You are also going to need some notes. I'll tell you what it is you need to write down, but in large part what you're going to be doing is kind of observing some things that our calculators show us and kind of learning to read the equation a little bit better. Okay, so let's get started. All right, first thing, I want you to take your calculators and I want you to enter the following two equations, and we're going to answer some questions on that here in just a moment. Okay, so everybody open up your calculator, go into your y equals menu, your equation editor, clear out any junk that happens to be there, and then type up your equations. Okay, once you got your equations typed up, go ahead and graph them. And let's consider a few things about these equations. Now, first, just in case you don't know, you've got of course, your calculator can handle up to 10 different equations in that equation editor. It's got y1, y2, all the way down y9, y0. Okay, so 10 different equations it can handle at once. It will graph them in order. So whatever you have typed in as y1, it'll graph that first. y2 will be second, and all the way down to y0 will be last. Now, if you forget which equation is which inside of the calculator screen, especially when you're answering a question that's got you comparing one graph to the other graph, what you can do to remind yourself which one is which is you can hit trace and it will activate that little Xbox cursor. And I think we all know that you can press left and right and that little cursor will move all over the graph. But also notice up at the top of the screen what it's telling you. Currently, like mine is on this lower of the two lines and it says y1 equals x. It's telling me which equation it's currently sitting on. It's sitting on the y1 equation. Okay, and if you use the up or the down arrow keys, it will move the cursor from one equation to the other equation. And now it's telling me that it's on the y2 equation. And this would be the case if you had 10 different equations in there. You could keep pressing up, 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 and it would switch to y2, y3, y4, y5. So you can kind of refresh your memory on which equation is actually which inside of your graph. Okay, now based on that, have a look at your calculator screen. Okay, and let's answer the question. What is the change that happened in the graph in between the equation that we've got typed for y1 and the equation we've got typed for y2? What's the difference? One's higher than the other. Now, which is higher? Okay, the one that we've got typed as y2 is higher, right? So the one that was y1 was actually passing through the origin, and the one that was y2, it got moved up 2 units. Okay, got moved up 2 units. That's actually going to be important here in a second. Okay. Now, what did we just say? Where was the coordinate of the y-intercept? Where's the y-intercept on the first equation? Okay, I'm not getting any answers. Have a look at your graph. Where's it crossing the y-axis at? The first equation? Yeah, if we switch down to the first equation, y1, it crosses the origin, right? So what's the coordinate of the y-intercept? 0, 0. That's the origin. Okay. What's the coordinate of the y-intercept for the second equation, which we got an answer for just a moment ago. Now we need it. Okay. And there it is, 0, 2. Okay. Now, did you notice anything about these y-intercepts? Okay. This is where it crossed the y-axis at. This is where this one crossed the y-axis at. Can you notice anything in this equation? And in this equation? Equation 1 basically says y equals x plus 0. Equation 2 says y equals x plus 2. Okay? That's not a coincidence. Okay, we'll predict the coordinate of the y-intercept for y equals x minus 3. Where is this one going to cross the y-axis at? At negative 3. Exactly. Okay, exactly. You can read the y-intercept out of an equation simply by looking at the equation. Okay, now let's see if the same information holds true for quadratic equations that we're working with now. Okay, so go into your equation editor and clear out those two equations that we put in a moment ago, and let's have a look at these quadratics. If you're not familiar, you've got a little squared button over on the left side of the calculator, fifth button down on the left. And of course, keep in mind that your subtraction button is this big guy over here on the right side in the middle of the addition, subtraction, multiplication, division. This little guy down at the bottom is a negative sign. Okay, we only use that negative sign if we're trying to lead off an expression with a negative value. All right, once you've got your equations, go ahead and hit your graph. Okay. Obviously, we're looking at parabolas this time rather than lines. Okay, well, have a look in your graph. What's the coordinate of your y-intercept for y1? Is it at the origin again? Okay. How about your coordinate of your y-intercept for y2? 0, 4. Is it 4? Negative 4. Good. Okay. Notice anything? Aside from my messed up board, not drawing things correctly. The first equation, x squared plus how much? Nothing. Second equation, x squared minus 4. Exactly where the y-intercept is at, negative 4. Okay, so tell me, predict the coordinate of the y-intercept for y equals x squared plus 26. Where will it be at? 0, comma, 26. Exactly. Okay. Now, what you're going to find is that this is going to hold true for everything. So here is something we need to write down in our notes. What statement can we make about what adding or subtracting a value to or from a parent function does? Okay, what statement can we make about this? When we add or subtract a value to the parent function, what does it do? Vertically. Okay, so our statement that goes along with this, what statement can we make about what adding or subtracting a value to or from a parent function does? Okay, specifically, what we're going to say is it causes a vertical shift in the graph, which is to say that it doesn't change the behavior of the graph. All it does is move it up or down. And you will find this to be true for any equation, any function that you ever come across in mathematics. It doesn't matter if it's a line or a parabola or a cubic or square root or absolute value or any other thing that you can imagine. If you change the value that's being added or subtracted to the overall function, all you're doing is moving it up or down by however much that value says. That's an important thing to be able to recognize, because whether you realize it or not, there are going to be questions that you're likely to see on your end of course test where it will ask you what is the difference in the graphs if you change this value, okay, from one number to another number. A lot of people go to their calculators and start typing things up and try to figure out what the graphs look like. Well, you don't even need the calculator for something like that. If they want to change this value for C, all they're doing is moving it up or down in the graph. That's all that they're doing. All right, now let's look at some different changes that can be made to the equations. I want you to go back to your calculator again. I want you to clear out whatever entries you have, and we're going to instead enter these three guys. Go ahead and graph your equations. And we end up with these three linear graphs. Now let's look and see. Compare graph y1 and graph y2. What change is made from y1 to y2? Okay, now if you can't remember which is which, again, remember you can use the trace function, okay, to move from one graph to the other. Now, unfortunately, all three graphs go through the origin. So as you try to move from one graph to the other by using the up and the down arrow keys, it's going to switch equations without actually moving the cursor anywhere because it's sitting in exactly the same place in all three times. Okay, so what you may want to do is scroll your cursor a little bit to the side so when you do switch graphs, you can actually see which graph it's on. Right now, my cursor is sitting on the equation y1. Okay, the question's asking what change was made in the graph from y1 to y2. Well, let's find y2. Okay, there it is. Okay, so switching from y1 to y2, what change is made as you go from y1 to y2? Okay, how would you explain that in plain English? Actually, okay, so there's some different vocabulary that we're kind of getting in the classroom here about what's the difference between equation 1, which is that equation right there that the Xbox is on now, and the equation 2, which the Xbox is on now. Okay, and kind of in plain English, the best way to describe it is that y2 is steeper than y1. It's in more of a hurry vertically. Okay, and that's exactly what it is. C-scope has a language issue of wanting to say that it is stretched in the vertical direction. And all of those are decent explanations. Okay, steeper, okay, is one way to explain it. More stretched in the y direction, okay, or that it's in more of a hurry. Okay, different ways of explaining it. Okay, but that's important. Okay, we changed a value in the equation and it caused the graph to be steeper than it was before. Okay, now let's look back at the calculator again. What changes made when we went from y2 to y3? Okay, I've currently my cursor sitting on y2. Okay, what is so different between y2 and y3, which is there? This one versus that one. What's the big difference? Quite obviously, one of them is pitched upwards as you read the graph from left to right. And that's how we read our graphs, is from as you move in the graph from left to right on the x-axis. One of them is heading upward, the other one is heading downward. Okay, so absolutely, what change is made in the graph? Okay, it's upside down. And the word that you'll hear used a bunch is that it is inverted, except I just misspelled it. Okay, that the graph has been inverted. Okay, so again, another change was made to the equation and it caused the graph to become upside down compared to what it used to be. Okay, so without using your calculator or anything like that, just consider the equation y equals negative 4x. Let's see if we can figure out what we would expect from this graph. Okay, it says y equals negative. Is this a graph we expect to be going up from left to right, like the first two were? Or is it going down from left to right, like the last one was? Okay, it's going to be going down. What we should expect is an inverted graph, or upside down, meaning it's falling from left to right. Okay. How about this 4 here? As the number gets bigger and bigger in front of x, what do you expect the graph to be doing? Is it in a bigger hurry going up? Or is it going to be, real lazy about it, very slow going upward? Well, think about what happened was the difference in between the first equation and the second equation. Did the graph get to be in a bigger hurry when we changed it to a bigger number? Or did it slow down when we changed it to a bigger number? What did it actually do? Got to be in a bigger hurry, didn't it? It got steeper when the number got bigger. Okay, so that would be another way of putting it. It'd be get steeper, or it would be more stretched, is what the language you're going to hear C-scope use a bunch. Okay, as the number in front of x gets larger and larger and larger, the graph gets stretched vertically. As the number gets smaller and smaller and smaller, it's actually going to get more flattened out. Okay. Now that's how it worked with lines. Let's clear out our calculators again and let's look at some parabolas and see what happens here. Okay, so go back into your equation editor, clear out those lines that we had, and let's type up these quadratics. Remember that when you're typing a fraction, it's just a division problem, so 1 divided by 2 on that last equation. After you've got them typed up, go ahead and graph them. Let's have a look. Okay. Clearly there are some differences in the graphs here. Let's have a look at the questions that are following. What change is made in the graph from y1 to y2? Okay, well, again, if you can't remember which one is which, that's fine. Okay, just go into your zoom. I'm sorry, my trace, not zoom. Okay, you may want to scooch over, get away from the origin a little bit since all the graphs are piled on top of each other. Okay, there's, as the top of the calculator says, there's y1, and there's y2. Okay, so y1 and y2 are the two guys that are side by side with each other up there in quadrant 1 and quadrant 2. Okay. Now, if you're paying attention, what you're going to notice is that the y1 equation is wider. Okay. So what change is made in the graph of y1 to y2? y2 got skinnier, didn't it? Okay. Or as C-scope has a habit of putting it, y2 became more stretched. And when they talk about stretched, they're talking about the y value. The graph is being pulled upward more quickly than it was before. Is what they mean by stretching it. Okay. What change was made in the graph from y2 to y3? Okay, we'll have a look back. Okay. y2 was that guy, the one on the inside up top, and y3 was the guy that's downward, quadrants 3 and 4. Okay. Now, obviously, it's going downward instead of upwards. Okay. Remember, that's the same thing we saw just a moment ago. The sign changed. Okay. So what change is made? The graph is going downward. Okay. Another word for that is it is inverted. And what else happened when that number changed from being a whole number into being a fraction smaller than 1? What happened to the graph? Okay. Do you notice that it's wider than either of the other two? Okay. You see that it's wider? Okay. So what you should be seeing in your graph is that the graph isn't becoming more stretched as the fraction in front of that variable is getting smaller and smaller. Okay. the graph is actually being flattened. It's not being pulled in the y direction so much anymore. It's being allowed to become slower. Okay, so what C-scope will call that is they're going to call it being flattened, if I could learn to spell. It's being flattened, meaning the y value is not it's not being pulled so hard in the y direction. It's taking a slower amount of time for it to open up. Okay, so if those facts are true, okay, now let's consider what the equation y equals 1/4 x squared would do. Is this graph going to be inverted? It's going to be upside down? No, it won't. Why was this one not going to be upside down? It's positive. That's right. Okay, so this one's going to be right side up. Is this one going to be stretched in the y direction or flattened or what? It's going to be flattened, right? As this number, this coefficient in front of x squared, as it becomes closer and closer and closer to 0, it is allowing itself to be flattened out. The graph is not in as much of a hurry on the y-axis as it would have been if these were bigger numbers. Okay, so now just like before, let's see if we can make a statement, or actually a couple of statements here, according to what we can predict about this number that sits in front of the independent variable. Okay, what two statements can we make about what multiplying a value by the independent variable does? Okay, as for this value that sits in front of our independent variable, we just saw that it does two things. First, it controls whether the graph is upside down or not. Positive would mean the graph is going to be right side up. Negative would mean the graph is inverted, or it's going to be upside down. And we can read that right out of the equation. Okay. The second thing that we determined is we can decide if the graph is going to be stretched or if it's going to be flattened. And we can make that determination by asking ourselves, is that number, or if we wanted to put it in terms of the equation we got up there, is the a number that is greater than 1, or is the a number that is smaller than 1? Okay. If it's a number that's greater than 1, then that means the graph is going to be stretched. Okay, the graph's going to be stretched. It's in a bigger hurry on the y-axis. Okay, it's going to do whatever it does much faster. If it's a number that's smaller than 1, then that means the graph is going to be flattened. Or another way of putting it is that it's not going to be in as big of a hurry. Okay, it's going to do what it's doing much slower. All right, now what I'm going to do is I'm going to give you some equations. You don't really need to write any of this down. I just want you to follow along and answer the questions that are up on the board with each equation that comes with it. So let's have a look at some. Okay, here's an equation. Y equals 3x. Okay, we're going to answer these questions. Okay, first off, what will this equation graph? Is it a line? Is it a parabola? What is it? It's a line. How do you know that this is going to graph a line? Yeah, y to the first, x to the first. When both of the variables are in the first dimension, that is going to graph a line. Okay. Is this a parent function? Okay. Well, how do you know if you're dealing with a parent function or not? Say again? Yeah, the equation hasn't been messed with in any way. Nothing has been changed to the graph itself. It's not stretched, it's not flattened, it's not upside down, or it's not moved up, it's not moved down, anything like that. Is this a parent function? Okay. Why is it not a parent function? The number in front of x needs to be a positive 1, and it's not. Okay, so this graph has been stretched, and we'll get to that here in a second. Has the graph been moved vertically? No. How do you know it hasn't been moved vertically? Yeah, is there a number added or subtracted onto the equation at the end? It's not. So this graph passes through the origin, so it has not been moved. Has it been stretched or compressed vertically? Yes, it has. We already said that. What has it been? Has it been stretched out or has it been flattened out? Yeah, it's been stretched, okay, because of the 3. Okay, so the answer would be yes, and more specifically, it's been stretched. Has it been inverted? Inverted would be upside down. No, it's not upside down. It's not inverted because that 3 that's there is a positive 3. If it had been a negative 3, that would be upside down. These are the questions we need to learn to be able to answer just by looking at these equations. Let's look at another one. Y equals negative 4x squared plus 3. What will this equation graph? Is this a line or a parabola or what? This one's a parabola. How do you know it's a parabola? Yeah. With a parabola, you're going to get one variable to the first power, another variable to the second power. Okay, the ones we're going to be looking at, it's always going to be y to the first x squared. Okay, you will find out later on it is possible to have it the other way around, but we won't see that. Is it a parent function? No, definitely not. This one has all kinds of changes going on in its equation, not a parent function. Has it been moved vertically? Okay, it has. Okay, where has it been moved? Has it been moved up or down or what? It's been moved up. Okay, it's moved up how far? 3 units because of that plus 3. Has it been stretched or compressed vertically? What do you think? Is this number a 1? No, the number in front of our independent variable is not a 1. So yes, it has been stretched or compressed vertically. Which is it? Has it been stretched or compressed? Remember, if it's a number bigger than 1, then that is a stretch. Okay, it's moving faster on the y-axis than it used to. Okay, has it been inverted? Yes, it has. It is a negative value that's sitting in front of our x, so it's upside down. Okay. How about this one? Y equals 1/2 x squared minus 7. What's it going to graph? Parabola, absolutely. Is it a parent function? Okay. Is it a parent function? No. Why is it not a parent function? It has all kinds of stuff being adjusted to it. Has it been moved vertically? Yes, it has. Which way? Yeah, down this time. How far? 7 units, absolutely. Has it been stretched or compressed vertically? Yes, it has. Which is it? Stretched, compressed, what? This time compressed. The number in front of our independent variable is smaller than 1. Okay, so our graph's going to be a little slower to do what it was normally doing. Has it been inverted? Nope. Positive 1/2, so it is not upside down. One more. Y equals x squared. What will it graph? Parabola. Parabola because you got one variable in one dimension, one in the other. Is this a parent function? This is a parent function. There is nothing changed about it. Has it been moved vertically? No, it hasn't. Has it been stretched or compressed? No, it hasn't. Has it been inverted? No, it hasn't. When all this is no, that's a parent function. Okay? Parent function is not changed. It's not stretched, it's not compressed, it's not upside down, and it has not been moved up or down the y-axis. Okay? So that's how it works. Okay, this is what the assignment is going to be about. You will not need calculators in order to do it because all you're going to be doing is reading the equations and making decisions on how the things or how the functions have been changed according to the changes in the worksheet.